Hi there, I'm Dr. McFerrin with DM Explains. In this video, I'm going to talk to you about phase lead compensation, which is our first type of controller we're going to look at, which looks at the frequency response to determine control performance. If you remember from the previous video about frequency response and stability, link in the upper corner, you'll remember that the example that we did with g of s equal to 1000 over s cubed plus 11s squared plus 10s, we got a gain margin of around negative 20 decibels and a phase margin of negative 34 degrees, which means that the system was unstable. Now, before we think about how we might improve this, the first thing I want to point out is that we can use a nice rule of thumb. We can use a really nice rule of thumb for system stability. That rule of thumb is that we want the gain margin in decibels to be greater than 6 decibels. And the reason that we want that, 6 decibels is a factor of 2. So we want to make sure that we won't have a significant issue there. And we want phi PM typically to be greater than 30 degrees. And the reason that we want this is to avoid any major disturbances or instrument errors causing the system to become unstable. With this in mind, I'm wondering if we could reduce the gain of that system to try to achieve that rule of thumb. So what I'm going to do is I'm going to multiply the system by 0.05. So then g of s would be equal to 0.05 times 1000 over s cubed plus 11s squared plus 10s. The reason I am choosing this is that k gain margin was 1/10, which is 0.1. If I want to make this even more stable, I could reduce k by another factor of 2 to try to hit my 6 decibels. So let's hop over to MATLAB and check it out. So what I'll do is I'll take the margin of the transfer function of 0.05 times 1000, that's my numerator, and my denominator will be 1, 11, 10, 0. Close my parentheses, hit enter, and see what happens. What I get is a gain margin of 6.85 decibels. That meets my rule of thumb, and a phase margin of 13.6 degrees. I know that this tells me that the gain margin is 6.85 dB. Great, meets my rule of thumb, but the phase margin is 13.6 degrees, which is definitely less than 30 degrees, so that does not meet my rule of thumb. If I desire a specific phase, what I could do is attempt to add more phase specifically at that point. So if we add more phase at that problem spot, we actually get what's called a phase lead compensator. A phase lead compensator means that it's going to give us an increase in phase. That's what the lead part means. GC of S, my compensator transfer function, is going to equal to K times tau S plus 1 over alpha tau S plus 1, and alpha has to be less than 1. The Bode plot version of this looks roughly like this. So if this is omega, we'll start with the magnitude of GC of S in decibels. I start from 20 log base 10 of K, and then at a certain frequency, which I'll tell you in a moment, it goes up in magnitude, and at another frequency it will turn off and flatten out. The phase corresponding looks something like this. So the specific frequencies in question here, first of all, I have a middle frequency, omega m. We can call it the midpoint frequency. The start of the increase in magnitude happens at 1 over tau, and the end happens at 1 over alpha tau. And what this will do is it will add an extra phase, which I'll call phi m, at omega m. So this might help with my issue. So omega m, my midpoint frequency is 1 over tau, square root of alpha. Alpha is 1 minus the sine of phi m over 1 plus the sine of phi m. If phi is in degrees, then I need to make sure this is also in degrees. And so what I'll choose to do is I'll choose to set 1 over tau equal to omega m square root of alpha, and 1 over alpha tau to be omega m over the square root of alpha. So in our example, k is 0.05, and from that Bode margin diagram, I found a value of the phase margin as 13.6 degrees, and it's at a specific frequency, 2.1 radians per second. So what I want to do is I want to set omega m to be that 2.1 radians per second, and then what I'll do is I'll add extra phase. For now, let's just try to add enough phase to guarantee the phase margin is bigger than 30%. Right now it's 13%. If I choose 30 degrees equal to phi m, then alpha is 1 minus the sine of 30 degrees over 1 plus the sine of 30 degrees, and that's equal to 0.33. That means that tau is 1 over omega m square root of alpha. That's 0.825. The result is that GC of S, my compensator, is 0.05, 0.825 S plus 1 over 0.33 times 0.825 S plus 1. And so what I'm going to do is go back to MATLAB and try this out. Okay, so now I'm going to repeat that margin command, except I'm going to add a new GC in there. GC is equal to the transfer function of 0.05 times 0.825, 1. In the denominator, I've got 0.33 times 0.825, 1. I'll take the margin of the series connection of the original transfer function, series of this, with GC, and then check, hit enter. And now what I get is a new gain margin. The new gain margin is equal to 9.67 decibels, still bigger than the 6 decibels I'm aiming for. And the phase margin is 29.3 degrees, which isn't quite what I want, but what I could do is I could increase the amount of phase I add to make this work. This yields a gain margin of 9.67 decibels and a phase margin of 29.3 degrees, which is pretty close to the 30 degrees I was hoping for. So let's look at a couple important properties of a phase lead compensator. The first important property is that it improves the transient response. And if I look at the compensator, what I should identify is that I'm going to get a 0, which is located pretty close to the j omega axis. And so the 0 is dominating. It sort of looks like the derivative part of a PID controller. And it's actually better than the derivative part because it doesn't have a 0 located at 0, which affects the magnitude and phase for all frequencies. The second part of this is that it has little to no impact on steady state error. And thirdly, this acts like a high pass filter. So what it does is it will potentially attenuate low frequency stuff but allow higher frequency stuff to pass just fine. So let's look at the design procedure for phase lead. Step 1 is to choose K to meet my steady state error specifications. We'll see how to do this in a little bit. Second, we're going to find the Bode plot of the system, K times the actual plant. And from this I want to find the phase margin and the frequency at which I measure that phase margin. Step 3 is to determine the extra amount of phase to increase the phase margin. Typically my approach is to get additional phase required plus 15 degrees. So what I do is I set phi m equal to additional phase plus 15%. Then I calculate alpha. Alpha is 1 minus the sine of phi m in degrees over 1 plus the sine of phi m in degrees. Then step 4 is to determine tau from specifying omega m equal to the new gain crossover. This sometimes takes some trial and error, but notably tau is equal to 1 over omega m square root of alpha. Typically what I do is I start with the value omega m equal to omega pm and then work from there. I will iterate if needed if I don't meet the requirements I want. At this point what I'd like to do is apply this to an example. I want you to find GC of S, a compensator that is phase lead such that ESS is less than 0.1 due to a ramp and the phase margin is greater than 45 degrees. The plant G of S is equal to 1 over S plus 1. So the first thing I do is find K to meet the steady state error specs. ESS is 1 over KV, which is equal to 1 over the limit as S approaches 0 of, and this will take some space. To get KV I multiply by S, and I've got K tau S plus 1 over alpha tau S plus 1. And then that's multiplied by G of S, 1 over S plus 1. If I evaluate this, I see that this is a type 1 system, and so those S's will cancel. As S approaches 0, tau S becomes 0, alpha tau S becomes 0, S becomes 0, and so what I'm left with is ESS is equal to 1 over K. And I want this to be less than 0.1, so K needs to be greater than 10. Step number 2 is to take the Bode plot of K, G of S, and find the margin. Let's let K equal to 11. So now I'm going to take the margin of 11 times the transfer function of 1, comma, and then it is 1 over S plus 1, so that's 1 over S squared plus S. So 1, 1, 0. Let's check that out. Okay, this tells me that the phase margin is equal to 17.1 degrees at 3.24 radians per second. So back to my handwritten notes. I know that PM is 17.1 degrees at 3.24 radians per second. Step 3 is to find phi m. Phi m is the additional phase needed, so 45 minus 17.1 plus 15 degrees. So that's going to equal to roughly 43 degrees. And then I calculate alpha. Alpha is 1 minus the sine of 43 degrees over 1 plus the sine of 43 degrees. I'll show you how to do that in MATLAB. So alpha is equal to 1 minus the sine degrees, so sin d of 43. I'm going to enclose that in parentheses. And then I'm going to divide this by 1 plus the sine degrees of 43. Again, enclose this in parentheses. So I get alpha is equal to 0.1891. Step 4 is to figure out what tau should be. Tau is calculated by taking 1 over omega m square root of alpha. That's equal to 1 over 3.24 times the square root of 0.1891. Going back to MATLAB, let's calculate that. Tau is equal to 1 divided by 3.24 divided by the square root of alpha. So tau is equal to 0.7098. So if I write this out, GC of S is equal to 11, 0.71, that's the rounded value of tau. S plus 1 over 0.19, 0.71, S plus 1. So now let's form GC. GC is equal to the transfer function of 11 times tau comma 1, and the denominator will have alpha times tau comma 1. And then what I want to do is I'll take the margin of the series of GC with my original transfer function and make sure to remove k here or you'll have a big accident. And so what I see is now I've got a gain margin, still infinite decibels. That's wonderful. But what I was caring about is my phase margin, which is 46.9 degrees, which is bigger than I needed. What I was looking for was a phase margin of 45 degrees. I have met that requirement. If you do a design problem like this and your first try doesn't get that, you may need to iterate to make your design meet the requirements that it needs. All right, that is all I have for this video. In the next video, we'll talk about the opposite of a phase lead compensator, which is a phase lag compensator. Thank you so much for watching, and we will see you next time. MATLAB dance break. Dun, 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 dun. MATLAB. Nope. Heh. We should though. Back over to MATLAB. Woohoo! Back in MATLAB, yeah. Back in MATLAB, yeah. Montage.